the speed of light is not just a number. It's the absolute edge of reality, a load-bearing wall of the universe, without which everything would collapse into chaos. We call it a limit, a barrier, a maximum. But in truth, it's the only thing that protects us from logical paradoxes that would destroy the very structure of cause and effect. At this boundary, time stops. The vacuum of space turns into an impenetrable wall of fire, and any attempt to cross it would mean the end of everything we know about existence. Today, we're going to explore why the speed of light is the foundation that holds reality together, and why, if we could somehow exceed this limit, the universe would simply cease to exist in the form we know it. Before we dive into this story about the nature of reality, make sure to subscribe to the channel and leave a like. That way, you won't miss other deep dives into cosmic mysteries that we explore every week. Now let's begin our journey to the very core of what makes anything possible at all. Imagine you're standing in the middle of an endless plain. In every direction stretches perfectly flat, empty space. You can walk anywhere, move in any direction, accelerate more and more. It feels like there's no reason you couldn't just keep speeding up forever. More energy, more speed. Seems obvious, right? But the universe is built differently. At some point, at a certain speed, something incredible happens. You slam into an invisible wall, not a physical barrier of stone or metal, but something far more fundamental. This wall is built into the fabric of space and time itself. That wall is the speed of light, about 300,000 kilometers per second. And the closer you get to it, the harder the universe fights back against your attempts to go faster. At first, people thought this was just an engineering problem. More power, more speed. Build better engines, burn more fuel, solve the issue. But when physicists in the 20th century looked deeper, they realized something terrifying. The speed of light isn't a technical limitation of our engines. It's an absolute law of nature. More than that, it's a defense mechanism of reality. Without it, the universe simply could not exist. Causes would happen after their effects. Time could flow backward. Logic would break. Atoms couldn't hold together. Life would be impossible. Everything would dissolve into senseless chaos. The speed of light isn't just the fastest you can go. It's the border between existence and non-existence, the edge of reality. And today, we're going to understand why this boundary exists, what happens to anything that tries to approach it, and why crossing it is not just technically impossible, but logically meaningless. We'll see why the speed of light is the load-bearing wall of the cosmos. Remove it, and everything falls apart. Let's start at the beginning, from the moment humanity first wondered how fast light actually moves. For a long time, people thought light was instantaneous. You open your eyes and immediately see the world. You light a torch, and the cave is illuminated at once. No visible delay. Ancient philosophers imagined light as a special substance that didn't need time to travel. It was just there, everywhere, immediately. But some people doubted that. Greek thinkers like Aristotle discussed the nature of light, but they had no way to measure its speed. The first serious attempt came much later. One of the first to doubt the instant nature of light was Galileo Galilei in the 17th century. He proposed a simple experiment. Two observers with covered lanterns stand on hilltops a few kilometers apart. The first opens his lantern. As soon as the second sees the light, he opens his own. The first measures the time between opening his lantern and seeing the response. Galileo and his assistants actually tried this on hills near Florence. They saw no delay, at least none their instruments could detect. The speed of light was simply too high for that era. He didn't measure the speed, but he asked the right question. Is the speed of light finite at all? The real breakthrough came in 1676. The Danish astronomer Ole Romer was studying the motion of Jupiter's moon Io. Io orbits Jupiter with a very regular period and often passes into the planet's shadow. These eclipses can be timed from Earth. Romer noticed something strange. When Earth was closer to Jupiter in its orbit, Io's eclipses occurred slightly earlier than predicted. When Earth was farther away, the eclipses were delayed. The difference built up to about 22 minutes over half a year. Romer realized what was going on. Light is not instantaneous. It takes time to travel from Jupiter to Earth. When Earth is closer, light arrives faster. When farther, it arrives slower. The difference in distance is about the diameter of Earth's orbit, roughly 300 million kilometers. Dividing this distance by the time delay, he made the first estimate of the speed of light. The number was huge, on the order of hundreds of thousands of kilometers per second. Not accurate by modern standards, but the key point was proven. Light has a finite speed. It is not instant. This changed our understanding of the universe completely. If light isn't instantaneous, then we never see distant objects as they are now, only as they were. Light from the sun takes about 8 minutes to reach Earth. We see the sun as it was 8 minutes ago. If it somehow vanished this instant, we wouldn't know for 8 minutes. Light from Proxima Centauri, our nearest star after the Sun, travels for about 4 years. We see it as it was 4 years in the past. The farther we look into space, the deeper we look into the past. In the 19th century, physicists began to understand what light actually is. James Clerk Maxwell unified electricity and magnetism into a single theory of electromagnetism. His equations showed how electric and magnetic fields generate each other and evolve in time. From these equations, something astonishing followed. Electric and magnetic fields can propagate through space as waves, and the speed of these waves was determined by fundamental constants describing electricity and magnetism. Maxwell calculated this speed, and it matched the measured speed of light. That was the moment of insight. Light is an electromagnetic wave. Oscillating electric fields create oscillating magnetic fields. Those generate new electric fields, and so on. This wave moves through space. Its speed depends on the properties of the vacuum, on how it responds to electric and magnetic fields, and this speed is the same for all electromagnetic waves. Visible light, radio waves, X-rays, they all propagate at this same maximum speed. But one huge question remained. Relative to what does light travel at this speed? Sound travels through air. Waves on water travel along the water's surface. So what does light travel through? In the 19th century, physicists proposed a special medium, the luminiferous ether. This light-bearing ether was supposed to fill all space, with light waves being vibrations of this medium. As Earth moved through the ether in its orbit, it should create an ether wind. That wind should slightly change the measured speed of light depending on direction. With the wind, one speed, against it, another. In 1887, Albert Michelson and Edward Morley performed their famous experiment using an extremely precise interferometer. A light beam was split into 2 perpendicular paths, reflected and recombined. Any tiny difference in light's speed along these paths would show up as a shift in the interference pattern. They measured at different times of year, with Earth moving in different directions through space. Result? Nothing. No shift. No ether wind. The speed of light was the same in all directions. Experiment after experiment confirmed the same thing. The speed of light is constant, regardless of the motion of the observer. This was a paradox. If you drive toward another car, your relative speeds add up. But if you fly toward a beam of light, its speed relative to you doesn't change. It still approaches you at the speed of light. How is that even possible? People tried to save the ether idea with various tricks. Maybe Earth drags the ether along with it. Maybe all objects physically contract in the direction of motion, canceling any effect. These explanations were ad hoc and unsatisfying. Something fundamental in classical physics just didn't fit. A new idea was needed. It came from an unknown patent clerk in Switzerland, Albert Einstein. In 1905, Einstein published a paper that changed physics forever on the electrodynamics of moving bodies. There were no references, no lengthy experimental discussion, just reasoning and thought experiments. Einstein proposed something radical. What if the speed of light really is the same for all observers, no matter how they move? What if that isn't a bug? It's a fundamental law of nature? From this simple postulate, he derived the entire special theory of relativity. The conclusions were shocking. If the speed of light is absolute and doesn't depend on the motion of the source or the observer, then space and time themselves can't be absolute. They must be relative. Time flows differently for observers who move at different speeds. Lengths contract along the direction of motion. Simultaneity becomes relative. Events that are simultaneous for one observer may not be simultaneous for another. It sounded insane, but the math worked perfectly, and everything was confirmed by experiment. Most importantly, the theory implied that the speed of light is not just the speed of electromagnetic waves. It's the ultimate speed limit for anything: objects, signals, interactions. Nothing in the universe can move faster than light. Not because our engines are weak, but because of the very structure of space-time. The speed of light is built into the fabric of reality as a fundamental constant. But why this particular speed? Why about 300,000 kilometers per second and not 1,000,000 or 10? From the point of view of physics, the exact number depends on our units. Meters and seconds are human inventions. In other units, the numeric value would change. Many physicists simply set the speed of light equal to 1 in their equations. It becomes the natural speed of causality, and everything else is slower. The important point isn't the number. It's that there is a maximum speed for cause and effect. But why is there a limit at all? Why does the universe forbid arbitrarily fast motion? To understand that, we have to see what happens as an object approaches the speed of light. Here, the drama really begins, because near this boundary, reality behaves in ways that are completely different from our everyday intuition. The first thing that happens as an object speeds up. Its mass increases. Not mass in the sense of what you read on a bathroom scale, but inertial mass, its resistance to acceleration. Imagine pushing a cart. It accelerates easily. Now imagine pushing a loaded truck. It accelerates much more slowly. more mass, more force needed for the same change in speed. As an object approaches the speed of light, its inertial mass increases. And not just increases, it races toward infinity. In Newtonian physics, if you apply a constant force, an object's speed increases steadily. The longer you push, the faster it goes. In relativity, it's different. At low speeds, everything feels almost Newtonian. But as you approach the speed of light, something changes. You keep applying the same force, but you get less and less acceleration. The energy you add no longer goes into increasing speed. It goes into increasing mass. At 90% of the speed of light, an object's mass is about twice its rest mass. At 99%, about 7 times. At 99.9%, roughly 22 times. The closer you get to the limit, the faster this growth explodes. At 99.99% of light speed, the mass is already tens of times greater. And what happens if you try to reach exactly the speed of light? The mass becomes infinite. And to accelerate something with infinite mass, you would need infinite energy. There is no infinite energy in the universe. The total energy of the cosmos is finite. So reaching the speed of light is impossible. Not just very hard. Not we don't yet have the technology, but physics itself forbids it. This also explains why light itself moves at light speed. Photons, the particles of light, have no rest mass. For them, traveling at the speed of light isn't a limit. It's the only possible mode of existence. They can't move slower. From the moment they're created, they move at light speed and always will. They don't accelerate or decelerate. They simply are at that speed. All particles with mass are forever stuck below this limit. The more massive they are, the harder it becomes to accelerate them. But mass is only the beginning. There's another strange effect at near light speeds. Time itself starts to behave differently. For a fast-moving object, time slows down. Not subjectively, but physically. Clocks on a fast spaceship tick more slowly than clocks on a stationary planet. This isn't an illusion. It's been confirmed in countless experiments. Imagine 2 twins. One stays on Earth. The other flies into space on a ship that accelerates to near the speed of light, travels to a distant star, then returns. For the astronaut, the journey takes a few years. He ages those years. But when he comes back, he finds that his twin on Earth has aged by decades. Why? Because time on the fast ship was running more slowly. The astronaut lived slower. His biology, his thoughts, his internal processes all slowed down relative to Earth. he didn't feel anything strange. His own time seemed normal to him. The time dilation is visible only to an external observer. This isn't just theory. For example, unstable particles called muons are created high in Earth's atmosphere by cosmic rays. At rest, muons decay extremely quickly, in millionths of a second. At light speed, that would only allow them to travel a few hundred meters. Yet our atmosphere is tens of kilometers thick, and we still detect muons at the surface. They shouldn't make it, but they do. Why? Because they travel at speeds close to light. Time for them slows down. From our point of view, they live much longer than their rest lifetime. From the muon's own point of view, its lifetime is still the same tiny fraction of a second. But the atmosphere is length contracted. The distance it has to cross shrinks dramatically along its direction of motion. Time dilation for the observer and length contraction for the traveler are two sides of the same coin. Space and time are intertwined. They form a single structure, space-time, and the structure deforms when you move. Now imagine what happens if we try to reach the actual speed of light. Time dilation becomes infinite. Time stops. For an object moving at light speed, no time passes at all. From a photon's perspective, its journey from the sun to Earth takes exactly 0 seconds. Its emission and absorption are the same instant. A photon does not experience time. It exists outside of it. This is another reason why objects with mass can't reach light speed. For them, this would mean the complete freezing of all processes, the end of their physical existence. But there's another effect, even stranger and less known. As an object accelerates harder and harder, trying to approach light speed, the surrounding vacuum begins to behave oddly. Empty space stops being empty. It becomes something else entirely. A kind of barrier, a wall of heat. This is known as the Unruh effect, one of the most unusual predictions of quantum field theory. In 1976, Canadian physicist William Unruh showed that for an accelerating observer, the vacuum appears not empty, but filled with thermal radiation. An accelerating observer perceives the vacuum as a hot bath of particles. A stationary observer in the same region sees nothing. They still see empty space. How can that be? In quantum field theory, the vacuum isn't really nothing. It's a seething ocean of virtual particles. Pairs of particle and antiparticle constantly flicker into existence and annihilate in unimaginably short times. These vacuum fluctuations are real and produce observable effects like the Casimir effect. Normally, these fluctuations average out. For a non-accelerating observer, the vacuum looks cold and empty, with temperature effectively at absolute zero. But for an accelerating observer, the story changes. Acceleration creates something analogous to a horizon, a boundary behind the accelerating object from which no signal can catch up with it. That region becomes causally inaccessible. This horizon affects vacuum fluctuations. Virtual particle pairs created near the horizon can no longer recombine. One falls beyond the horizon. The other remains outside. For the accelerating observer, these leftover particles form real radiation, thermal radiation. The stronger the acceleration, the higher the UNRRA temperature of the vacuum. For everyday accelerations, the effect is unimaginably tiny. The UNRRA temperature for an acceleration of 10 meters per second squared is effectively zero. It's impossible to detect in the lab with current technology. But for an object trying to reach near light speeds, the required acceleration becomes enormous, and the UNRRA effect becomes significant. The vacuum turns into a wall of fire. Imagine a spaceship trying to accelerate to a significant fraction of light speed. At first, everything is fine. Engines fire, the ship speeds up. But the faster it goes, the harder it becomes to gain more speed. Mass increases, requiring more and more energy. You push the engines harder. Acceleration grows. And then the crew notices a strange glow ahead. The vacuum itself begins to shine. The empty space in front of the ship seems filled with radiation. The ship heats up, not from friction with gas, but from the vacuum itself. The emptiness has turned into a furnace. This is the UNRRA effect in action. The stronger the acceleration, the hotter this vacuum heat becomes. And the closer you try to get to the speed of light, the greater the acceleration you need to add just a bit more speed. Acceleration skyrockets, and with it, the UNRRA temperature. In the limit, as you try to reach light speed, the temperature becomes infinite. The vacuum becomes an impenetrable wall of radiation. Another protection mechanism. Another way the universe says, you cannot go further. The UNRRA effect hasn't yet been directly measured. It requires absurdly large accelerations, but it's closely related to Hawking radiation, the predicted radiation of black holes. Hawking radiation also arises from vacuum fluctuations near an event horizon and has indirect support. The UNRRA effect and Hawking radiation are two sides of the same physics. If Hawking radiation is real, the UNRRA effect almost certainly is too. So we see three barriers that prevent anything from surpassing the speed of light. 1. Infinite growth of mass requires infinite energy. 2. Infinite time dilation. Time stops. 3. vacuum turns into a wall of fire, lethal radiation. All of these are physical barriers. But there is another one, even deeper: causality. Causality is the principle that causes always precede effects. You pull the trigger, then the bullet leaves the gun. You throw a stone, then the window shatters. The order of events matters, and this order is governed by how fast influences, signals, information, interactions can propagate. Nothing can transmit influence faster than light, because if it could, the order of events would depend on who is watching. For one observer, the cause could come before the effect. For another, the effect could come before the cause. This would destroy logic. Imagine you can send a signal faster than light. From your frame, you press a button, and an instant signal reaches a distant planet. For you, the sending and receiving are simultaneous, but simultaneity is relative. For an observer moving relative to you, these events can occur in a different order. For them, the signal arrives before you send it. Already weird, but it gets worse. If that second observer can also send a superluminal signal back, then in some frames, their reply can reach you before you sent the original message. You receive an answer to a question you haven't asked yet. This creates a causal loop. Information travels in a closed circle through time. The effect becomes the cause of itself. Paradoxes appear. The classic example is the grandfather paradox. You travel into the past and kill your grandfather before he meets your grandmother. Then your parent is never born. Then you are never born. Then you cannot travel into the past. Then your grandfather is never killed. Then you are born. Then you travel back. An endless logical contradiction. Special relativity forbids such causal loops, not because physicists dislike paradoxes, but because they are incompatible with the geometry of space-time itself. As long as the speed of light is an absolute limit, signals can only travel within something called a light cone. Your future light cone is the region of space-time that you can influence. Your past light cone is the region of events that can influence you. These cones never bend into closed loops. There is no way to send a signal outside the cone and loop back into your own past. Causality is protected. But if you could move faster than light, the light cone structure breaks. You could jump outside your cone into regions that shouldn't be causally connected to you, and then return to your own past. Cause and effect become frame-dependent, and paradoxes become unavoidable. The universe loses logical consistency. Events can happen without causes. Causes can vanish after their effects. reality collapses into nonsense. Physicists have tried to find loopholes, some way to allow faster than light travel without breaking causality. Could there be exotic configurations of space-time that let you effectively move faster than light, but keep logic intact? So far, every attempt has run into the same wall. Either causality is broken, or you need something that appears impossible. Negative energy, exotic matter, infinite resources. The universe defends its speed limit ruthlessly. The speed of light is not just a limit. It's a protection mechanism. Without it, reality could not exist. Let's imagine, just for a moment, a universe with no speed limit, where interactions spread instantly. At first, it sounds convenient. No delays. Press a button here, and the effect appears there immediately. Instant communication across any distance. Interstellar travel becomes trivial. But dig a little deeper. Without a speed limit, there is no relativity of time. Time becomes absolute. Space becomes absolute. Simultaneity is the same for everyone. Sounds simple. But then Maxwell's equations no longer work the way they do. Electromagnetism requires a finite propagation speed. Without it, electromagnetic waves, and thus light itself as we know it, wouldn't exist. Electrons couldn't orbit nuclei the way they do. Atoms, as we know them, wouldn't be stable. Matter would fall apart. Suppose, for the sake of argument, that some radically different physics restores stable matter with infinite signal speed. Even then, causality is in trouble, because instant in one frame is not instant in another moving frame. You can still build causal loops and paradoxes. The universe loses a consistent arrow of time and a consistent structure of cause and effect. The speed of light isn't a mere nuisance. It's the spine of the universe. It supports causality, time, space, electromagnetism, the structure of matter. Everything depends on this emmet. This isn't an engineering challenge that we can hack with better tech. It's a fundamental principle. Remove it, and the physical world stops making sense. Of course, humans don't like the word impossible, especially when it comes to space. The universe is enormous. Distances between stars are measured in light years. To the nearest star system, about 4 light years. To the center of the galaxy, tens of thousands of light years. To Andromeda, over 2 million light years. Even if we could travel at light speed, these journeys would take years, centuries, millions of years. And we can't travel at light speed. Current technology gives us, at best, a tiny fraction of that. At those speeds, even reaching the nearest star would take tens of thousands of years. Interstellar travel looks hopeless. So people ask, is there any way to cheat? Not break the speed of light directly, but sidestep it somehow? Physicists have explored several speculative ideas. One popular option: wormholes. A wormhole is a hypothetical tunnel in space-time connecting two distant points. Imagine space as a sheet of paper. 2 points on the surface are far apart. To walk from one to the other, you'd traverse the long path across the sheet. But if you fold the sheet so the 2 points touch and pierce a hole through, you get a shortcut, a wormhole. Go through it, and you arrive at a distant place without crossing the distance in between. You didn't travel faster than light through space. You changed the geometry. Einstein's general theory of relativity allows wormhole-like solutions. Einstein and Rosen wrote about such structures in the 1930s. But there are problems. First, wormholes are unstable. They tend to collapse instantly. To hold a wormhole open, you'd need exotic matter with negative energy density. Matter that doesn't attract, but repels, pushing space apart and supporting the tunnel. Does such matter exist? Maybe in some quantum sense. The Casimir effect, for example, shows that vacuum energy can be negative in certain configurations. But scaling that up to macroscopic wormholes would require unimaginable control over quantum fields. Even if you somehow built a stable wormhole, there's a second problem. Wormholes can act as time machines. Take a wormhole with 2 mouths. Leave one mouth in place. Accelerate the other to near light speed and bring it back. Due to time dilation, less time passes near the traveling mouth than near the stationary one. The 2 mouths now disagree on what time it is. Step into the future mouth and exit the past one. You've traveled into the past. Causal loops and grandfather paradoxes return. Stephen Hawking proposed the chronology protection conjecture. Quantum effects near such configurations would grow without bound and destroy the wormhole before it can be used as a time machine. In other words, the universe protects its timeline. Third problem: assuming macroscopic wormholes exist. Where are they? They'd likely form at microscopic scales, embedded in quantum foam at the Planck length, far too small for anything to pass through. To enlarge one, again, you'd need absurd amounts of energy and exotic matter. Another famous idea is the warp drive. In 1994, Miguel Alcubierre proposed a solution to Einstein's equations, where a warp bubble of space-time moves faster than light relative to distant observers. Inside the bubble, a spaceship rests in flat space. In front of the bubble, space contracts. Behind it, space expands. The bubble surfs through The ship just sits in its bubble. But the bubble itself can move faster than light relative to distant points. It looks like a loophole, and mathematically, it's a valid solution. But again, there are issues. First, the Alcubierre drive requires negative energy, enormous amounts of it. Early estimates suggested energy equivalent to the mass of several stars in exotic form. Later refinements reduced the requirement, but it's still far beyond anything realistic. Second, the ship cannot control the bubble from inside. Inside the warp bubble, you're causally disconnected from its boundary. You can't send signals out to steer or stop it. How do you start or navigate such a drive? Third, radiation. As the bubble moves, it could sweep up high-energy particles. When the bubble stops, that energy would be released in a deadly blast ahead, like a cosmic bomb. Some more recent papers propose modified warp metrics that might avoid negative energy or reduce the energy requirement. But these ideas remain highly speculative. No one knows if any of them are physically realizable. People also point to quantum entanglement and teleportation. In entanglement, two particles share correlated states, and measuring one instantly determines the outcome of a measurement on the other, even across light years. It feels like information is traveling faster than light. But entanglement can't transmit usable information faster than light. You still need a classical signal, limited by the speed of light, to interpret the result. No superluminal messaging. Tachyons, hypothetical particles that always move faster than light, also show up in some theories. But if they exist, they almost inevitably lead to causality violations and paradoxes. Most physicists treat them as mathematical artifacts, not real particles. The pattern is clear. Every known attempt to circumvent the speed of light either breaks causality or demands physically impossible conditions. The speed of light isn't an engineering constraint. It's the edge of what it means to have a consistent reality. So, why is the universe so strict about this limit? To answer, we have to ask, what is space-time itself? In Newtonian physics, space and time are a stage, the neutral background on which events unfold. Matter moves, forces act, but space and time themselves are rigid and unaffected. General relativity changes that picture. Space-time is not a stage. It's an active, dynamic entity. Matter tells space-time how to curve. Curved space-time tells matter how to move. Gravity is geometry. But what is space-time made of? Is it fundamental or emergent from something deeper? Some theories, like string theory, suggest that at the smallest scales, space-time arises from vibrating strings in higher dimensions. Others, like loop quantum gravity, describe space-time as a network of discrete atoms of geometry. We don't yet know which picture is correct, but we do know this. Whatever space-time is, it has built-in rules. One of those rules is a maximum speed for disturbances in the fabric. The speed of light is that speed, the speed at which ripples in space-time and in the fields defined on it can propagate. Imagine a stretched membrane. If you pluck it, waves spread across the surface. The wave speed depends on the membrane's tension and density. It cannot be arbitrarily high. Similarly, the maximum speed of signals in space-time is set by its properties, encapsulated in constants like the electric permittivity and magnetic permeability of the vacuum. Combine them, and you get the speed of light. Those constants are tied to other fundamental constants: Planck's constant, the electron charge, Newton's gravitational constant, and so on. The universe is finely tuned. Change one constant significantly, and stars may not form. Atoms may not be stable, chemistry may not work, and life may never arise. Some speculate that the speed of light might vary on cosmological timescales, or that it was different in the early universe. But so far, all observations show that it has been constant over billions of years and across vast distances. It's a universal pillar of reality. Now let's take a step back and look at the philosophical side. The speed of light doesn't just limit how fast we move. It shapes causality. It defines what before and after mean. It creates the structure of time. Your past is the set of events that can influence you. Your future is the set of events you can influence. The boundary between them is drawn by light cones. Everything outside those cones is neither in your causal past nor in your causal future. It's elsewhere, causally disconnected from you. This means the universe is not a rigid, globally predetermined machine where everything is fixed from the start in an absolute sense. Instead, it's a web of local cause and effect chains that spread at finite speed, intersect, and intertwine. The finite speed of light allows complexity, branching possibilities, and emergent behavior. It creates room for structure, for life, for consciousness. A universe with infinite signal speed would be one giant, tightly coupled system. Every change would instantly affect everything. There would be no locality, no independent regions, no building blocks of complexity. It's doubtful anything like life could exist there. The speed of light builds walls that separate regions of space-time and give them partial independence. It creates islands where intricate structures can arise without immediate interference from the entire universe. Now, let's return to where we started. We began by calling the speed of light a wall a barrier, a limit. But a better metaphor is a foundation, a load-bearing wall. It holds everything else up. Without it, there is no structure, no logic, no time, no causality, no matter, no life. We can't exceed the speed of light, not because we're primitive or under-equipped, but because the question itself is ill-posed. It's like asking, what's north of the North Pole? North ends there. Beyond it, the concept stops making sense. The speed of light is the North Pole of motion. Beyond it, faster doesn't exist in any meaningful physical sense. Does this mean we're doomed to stay on Earth forever, with the stars forever out of reach? Not necessarily. There are still slow, but physically allowed, paths forward. Relativistic ships that travel at, say, 90 to 99% of light speed could, in principle, reach nearby stars. Due to time dilation, such journeys could be a few years long for the crew, even though decades or centuries pass on Earth. The travelers would become time-displaced, arriving in the future of their home world. Generation ships, enormous vessels where many generations live and die through a centuries-long voyage. Those who start the journey will never see the destination, but their descendants might. Cryosleep, or deep hibernation, if it ever becomes possible, might let a single crew sleep through such long journeys. Or another option: don't send people, send information. Self-replicating probes, carrying AI and blueprints for life, could seed distant systems, build infrastructure, even regenerate humans from stored genetic data, or create new intelligent beings. Whether we consider that us is another question. And finally, there's the most radical option. Accept the limit. Accept that the universe is huge, that the stars are beautiful and distant, and that our primary stage, at least for a long time, is our planet and our local system. One more perspective. The speed of light not only separates us, it may also protect us. If interstellar travel were easy, the galaxy might be full of conquest, conflict, and extinction. Our own history on Earth is filled with wars and invasions. Now imagine that writ large on a galactic scale. The enormous distances and the light speed limit act as a buffer. Civilizations, if they exist, are separated by both space and time. Each evolves largely in isolation. Maybe this isn't a bug, but a feature. We live at a time when humanity is just beginning to look outward. We've walked on the moon, sent probes to the planets, and stared with telescopes into the depths of the universe. We've realized how immense it is, how many stars and planets there are, and how tiny we are. There may be life out there, There may be civilizations, but we cannot reach them, and they cannot easily reach us. The speed of light divides us, but in doing so, it may also give us time to grow up. The constraints of physics teach us humility. They set boundaries that we cannot cross, no matter how loudly we demand it. They remind us that not everything is negotiable. Constraints are not always prisons. Often, they are frames. Inside frames, art becomes possible. Inside physical laws, life becomes possible. The speed of light is the frame of the universe, the most fundamental of all. It defines what can and cannot happen. It creates structure. It makes reality real. We started with a simple question: why can't we exceed the speed of light? The answer is because the speed of light is not just a speed. It's the speed of causality. It's the speed at which existence itself propagates. Nothing can happen faster than that, because happening is defined by how cause and effect spread, and that spreading is limited by the speed of light. Trying to move faster than light is like trying to move faster than time itself. But time cannot go faster than itself. The question self-destructs. So the universe defends this limit with everything it has. Mass becomes infinite. Time stops. Vacuum turns into fire. Causality breaks. All these are warning signs. Stop. There is nothing beyond this. We live on the safe side of that wall, inside a universe where laws hold, where causes produce effects, where the past shapes the present, and the present shapes the future, where matter is stable, where stars shine, where planets orbit, where life emerges, where consciousness contemplates itself. All of this is possible because there is a wall, because there is a limit, because there is the speed of light. We can see this wall as a prison that keeps us from the stars, or we can see it as a foundation, a structural beam that holds everything else. Without this wall, there would be no us, no universe, no reality. The speed of light is not just a number, not just 300,000 kilometers per second. It's a fundamental principle, the load-bearing wall of the cosmos, the thing that makes the universe a universe. We exist because this limit exists. We can think, feel, love, and create because space-time has structure, and that structure rests on the speed of light. It's not a prison, it's a home, a set of boundaries within which life is possible. When we look at the night sky and see the stars, we're seeing the past. Light from some of those stars has traveled for decades, centuries, millennia. Some may already be gone, but their light is still on the way. Because the speed of light is finite, we have a history. Time has direction. The universe has a story. From the Big Bang to now, from simplicity to complexity, from particles to planets, from chemistry to consciousness. We are part of that story. So the next time you see a beam of light, remember, you're looking not just at photons, you're looking at waves in the fabric of space-time. You're seeing the visible trace of the deepest rule in the universe. The speed of light is the universe's way of saying, these are the laws. These are the boundaries. Within them, almost anything is possible. Beyond them, nothing is. If you enjoyed this journey into the foundations of reality, don't forget to like the video and subscribe to the channel. We'll keep exploring the deepest mysteries of physics and the cosmos. And remember, every ray of light you see is the universe itself speaking. And the speed of that light is the wall that keeps reality standing.